The frame is narrow at first, a slit of metal opened by hands that never touch the stars themselves. A spectrograph feeds on faint light, taking what looks to the eye like a simple point in the sky and stretching it into a ladder of bars and gaps. The ladder is a secret language. When one bar deepens and another fades, the instrument has just told us what gases are boiling above the surface of a planet we will never step on. No travel is required. No spacecraft has landed. Only light has crossed the distance, and it is enough to transform suspicion into evidence. The visual is stark. A hot Jupiter, swollen to twice the size of our familiar giant, swings so close to its star that its day is locked, permanent, and merciless. Observers track a dark notch in starlight as the world passes in front. That notch is regular, precise, a beat kept by gravity. But when instruments trace the infrared glow, the hot point is misplaced. The brightest part of the planet is not where the star is overhead. It lingers, shifted, drawn sideways. Winds have stolen the heat and dragged it into night. The numbers are insistent. Iron vapor may rise on the dayside and condense in the cold of night, falling back as rain that no human ear could bear to hear. The paradox is real familiar weather, but made of metal. We try to name this kind of storm, but our language breaks. Rain is comfort, memory, the smell of soil after drought. But here, rain is shrapnel cooled just enough to solidify before striking unseen oceans of gas. If the universe allows this, what other certainties have we mistaken for universal? The gate has opened. The city of worlds is stranger than we thought. One by one, the gates unfold. The gate of light comes first. A planet transits its star, dimming it by a fraction thinner than a whisper. The dip repeats, and repetition is proof. From the depth we extract size, from the timing we extract orbit, from the wobble of the star we extract mass. Each is an equation carved into photons. Light becomes a scale, a yardstick, and a diary all at once. According to one research group, the transit method has now cataloged thousands of such worlds, each a point where light told the truth. The contradiction is that we expected the ordinary. Yet in the count of thousands, no true twin of Earth has been found. In plain terms, we learn to read planets the way we read pulse lines on a monitor. A curve rises, a curve falls. A sudden kink speaks of another body tugging in the dark. A faint glow when the planet slips behind the star reveals the heat of its dayside. Light is not merely illumination anymore. It is temperature, chemistry, and weather. Some teams even suggest subtle brightening events, candidates for cloud geometries so perfect that droplets must be spheres hanging for years. If this interpretation holds, then we are mapping not just orbits, but the architecture of alien clouds. The gate of heat follows. Instruments in the infrared show a planet that should blaze at noon. Instead, the hot point is smeared across longitude, caught in jet streams running at kilometers per second. The night is not entirely night. The day is not entirely day. Simply put, winds so strong they defy our imaginations are dragging daylight into darkness. On Earth, winds carry scents and dust. Out there they carry metal, methane, silicate ash. A contradiction rises. How can chemistry survive at such temperatures, yet the signals of methane and water remain? Life is not implied, but chemistry is stubborn. One published dataset reveals spectral lines consistent with molecules tearing and reforming in high-pressure furnaces. Think of it like this. Imagine walking through a storm where the raindrops are shards of glass, each propelled by a wind faster than sound. The blue sky you think you see is not an ocean's reflection. It is silica scattering light, a laboratory turned inside out. A planet once mistaken for a water world is revealed as a forge that paints itself in misleading colors. A schoolchild might say, blue means ocean. In the laboratory of space, blue can mean knives in the air. The lesson is clear. Names deceive. We test another gate, the gate of time, Some planets fall into the comfortable ring called the habitable zone, where liquid water might last, but stars brighten as they age. The safe ring drifts outward, turning paradise into steam. To put it another way, habitability is not a place, but a moving target. A planet discovered today as Earth-like may become a greenhouse in the stellar future. Some calculations show that even if orbit and size match, time erodes the safety. We ask, how many of our hopes are illusions caused by snapshots? How many are real? We stand before giants too distant, too large. For our textbooks, a planet 3 times the size of Jupiter glows faintly far from its star. By standard formation models, the materials should have been too thin for such a bulk to form. Yet it exists, imaged directly, a pink ember against the dark. What this means is that our diagrams of planet birth are incomplete. Either gas clumped by collapse without a core, or something else moved this object outward after birth. Some investigators argue for violent gravitational scattering. The contradiction is sharp. The universe is showing us results before we finish writing the rules. The gate of seasons defies another intuition. A star spins so quickly that it bulges at the equator, heating its poles more than its waste. A planet orbiting close does not receive steady light. Instead, it endures 2 summers and 2 winters per orbit, all packed into a day and a half. In everyday language, the star, not the planet, paints the seasons, the tilt of an axis. The rhythm we expect becomes secondary. What, then, is a season? A geometry, a motion, a coincidence. The gate of color tricks us again. TRES-2b reflects less than 1% of incoming light. It is darker than the blackest materials we manufacture. A world without reflection, almost erased from vision. Then another, GJ504b, shines in magenta, a hue rare among natural skies. Color here is not decoration but evidence. One research collaboration has suggested these shades encode chemical balances, particle sizes, and temperatures layered through atmosphere. If black can be measured and pink can be cataloged, then even darkness and brightness are data. Finally, we step to the gate of memory. In a globular cluster, orbiting both a pulsar and a white dwarf, a planet circles that is nearly as old as the galaxy itself. Its age is measured not in millions, but in billions stacked almost to the universe's birth. The planet is older than Earth by a factor of 3. It has seen suns flare and die, has circled a corpse star that ticks in radio waves. To put it another way, planets were present almost as soon as stars themselves. If such ancient survivors exist, then the window for stability is wider than we guessed. The contradiction is that life as we know it requires heavy elements. Yet this planet formed when those elements were scarce. What kind of chemistry writes survival across 13 billion years? Our micro-questions accumulate. Are we fooling ourselves by projecting Earth onto every new find? If blue can be rock dust, what else wears disguises? Can darkness be measured as a physical property, not just an absence? If seasons can come from the star, how much of climate is planetary at all? When a world can be older than continents, what does young Earth even mean in context? The scale remains human. Imagine a year so short you could live through 20 before your child finishes school. Imagine standing on a boundary line, daylight overhead, eternal night behind you, and metallic rain hissing on the horizon. Imagine counting seasons not by tilt, but by the star's bulge. Simply put, these are not inventions of myth. They are confirmed or proposed realities, written in data. One published team notes that measurements of secondary eclipses reveal temperatures so high that molecules are stripped apart. Another suggests that eccentric orbits like Whiplashes are carved by gravitational duels. A third has traced the faint color of a distant gas giant, verifying with direct imaging. Together, these studies remind us that exoplanet science is a ledger of contradictions tested by repeated observation. At its core, The hook is this: the more closely we look, the less normal survives. Our categories shrink, our rules bend. Every new planet is a gate that requires us to redraw our maps. We step through, and each passage leaves us more estranged from our old definitions, yet closer to the universe as it is. The City of Worlds is not orderly. It is a labyrinth where every corner reveals an exception, not a rule. If this wide view stirs your thinking, please like and subscribe to the Quiet Universe channel. We turn now toward the first of these gates, where light itself sketches rain made of iron and invites us to follow deeper into the catalog of impossible worlds. The story begins with a curve of light, a pattern as thin as the line a heartbeat makes on a monitor. Astronomers measure the dip, test it again, and watch the star blink with perfect rhythm. Each blink is a planet, each repetition a world orbiting far beyond our reach. The first clue is so small it seems fragile, but precision makes it solid. A few hundredths of a percent change in brightness is enough to tell us that something has crossed the star. The geometry is simple, but the consequences are vast. What seems like a tiny flicker becomes the outline of a globe. This is the world of JWST 6b, a giant planet clamped into a tight leash around its sun-like star. One side forever faces daylight, blasted by heat so intense that iron itself becomes vapor. The other side faces eternal night, where that vapor cools and condenses, falling back as rain made of metal. The contradiction is striking. We know rain as water falling gently to earth. Here rain is molten, searing, hardened in flight. Instruments on large telescopes have traced the chemistry of its atmosphere, hinting at iron signatures. According to one observing team, the spectral fingerprint is clear enough to match with models of condensation. In plain terms, imagine a storm cloud the size of a continent releasing not water but glowing iron droplets. The numbers confirm the conditions. Daylight temperatures exceed 2,400 degrees Celsius, hot enough to vaporize steel. As the winds drag this vapor across the planet's circumference, the temperature drops by more than 1,000 degrees. The vapor condenses, raining into the night sky. To us, it sounds like science fiction, but the measurements stand. They are checked against models, repeated across nights. Compared with different instruments, one research group reported consistent asymmetries in the spectral lines that mark the morning limb, a sign of uneven chemistry. Simply put, this is weather stretched to a scale and substance we cannot inhabit. On Earth, a storm may bring thunder and lightning. On this world, a storm brings showers of liquid iron that turn into pellets before hitting the unseen surface below. The paradox is not only about matter, but also about perception. What counts as normal weather if clouds can glow red and drizzle metal? The method that reveals this is deceptively delicate. A star dims by a fraction of a percent when the planet crosses. During those hours, light filters through the thin rim of atmosphere, and the gases leave fingerprints. We test the fingerprints against laboratory spectra, checking for sodium, potassium, water vapor, iron, titanium. The atmosphere becomes legible without ever being seen directly. As one published survey emphasized, transmission spectroscopy is our most powerful tool for worlds we cannot reach. The contradiction is that from such a faint signal, we draw pictures of storms. To put it another way, we build weather reports for places hundreds of light years away. Our forecasts speak not of umbrellas, but of vaporized metals. We map not cold fronts, but heat tides flowing at thousands of kilometers per hour. The irony is that the more alien the conditions, the clearer the lesson. Atmospheres are universal laboratories. Chemistry may vary, but the principles are shared. If iron can reign here, then other worlds may host storms beyond even these extremes. Think of it like this: you hold a prism in your hand. White light enters. Colors emerge. On Earth, it is a school experiment. On JWST 76b, the prism is a star, and the colors it shows us include lines carved by iron vapor. Our prism is many meters wide, made of glass polished to perfection, and it sits on a mountaintop. The light it catches has traveled for hundreds of years before touching the mirror. That light encodes a planet. The prism tells us its story. The next question arises naturally. If we can see iron rain through starlight, what else hides in those spectra? Could we detect weather driven by silicate dust or by exotic molecules? Some instruments already report hints of titanium oxide and vanadium oxide, gases that control heat by absorbing light. Are these reliable detections or artifacts of noise? One research collaboration has urged caution, noting that models can mimic signals. The debate continues. Yet the possibility remains atmospheres more complex than anything we predicted. Why does this matter? Because it shows us that even giants locked in fiery orbits are not static. They change, circulate, and redistribute heat in ways that challenge theory. If our models of atmospheric circulation fail here, can we trust them on smaller, cooler planets that might harbor life? Why does it matter that iron reigns in the dark? Because it teaches us that chemistry adapts, that stability is relative, that even in conditions hostile to life as we know it, processes still follow rules. Each storm is a lesson in planetary endurance. At its core, this is a triumph of indirect seeing. No eye will ever look down on WASP-76b's metallic horizon, but spectra let us stand in imagination on its night side, feeling the hiss of rain that would pierce steel. The measurements force us to revise what counts as a sky. If we once assumed that weather everywhere must echo our own, we were wrong. The universe insists on variety. Our rhetorical questions sharpen. What do we call rain when water is no longer part of it? How do we speak of storms when clouds are furnaces? If color can lie, can chemistry tell the truth? What counts as an ordinary climate when every new detection contradicts our Earth-centered categories? Human scale keeps the strangeness close. Imagine holding out your hand and catching not a drop of rain but a cooling shard of metal, still glowing from the heat of its journey. Imagine a night sky lit not by stars, but by sparks of falling iron. Imagine wind that could carry continents if they floated free. Simply put, these pictures help anchor numbers too vast for intuition. One publication has compared the energy redistribution on hot Jupiters to that of Earth's jet streams, magnified by orders of magnitude. Another has highlighted the detection of sodium absorption as a marker of atmospheric escape. Together, they remind us that the physics of motion and loss applies across scales. The contradiction is that in our search for habitable Earths, we first encounter uninhabitable infernos, yet they are essential teachers. Why does it matter? Because without testing physics in extremes, we cannot trust it in subtlety. A storm of iron confirms circulation theories. An atmosphere that holds or loses metals constrains models of escape. Each detail reduces uncertainty. Each confirmation strengthens the ladder we climb toward understanding rocky worlds. At the gate of iron rain, we pause, knowing that storms can be written in spectra, that weather can be deduced from dips in starlight. The bridge leads forward. If light can reveal liquid metal, what will pressure carve from carbon? The second gate in the City of Impossible Worlds opens onto a planet so close to its star that a year is shorter than a day on Earth. This is 55 Cancri E, a super-Earth orbiting in less than 18 hours. A globe larger than our own, but locked in a grip of heat and gravity that stretches the imagination. Observations suggest its surface bakes above 2,000 degrees Celsius, hot enough to melt rock. The question rises immediately. Can a planet this close hold an atmosphere at all? Or is it stripped bare to glowing stone? Some teams argue they have detected traces of gases, a tenuous shell clinging against the furnace. Others doubt, suggesting the signal belongs to magma seas radiating in infrared. The contradiction is unresolved, but the clues are enough to make us ask, what does a rocky planet become under such relentless pressure? One hypothesis has gripped both scientists and storytellers. If the planet formed from carbon-rich material, the pressures inside could force carbon into crystalline form. In plain terms, the very bedrock might be diamond, not jewelry, but layers of hardened lattice stretching thousands of kilometers down. The idea is not a fantasy. Laboratory experiments on Earth compress carbon under immense pressure, producing diamonds from graphite. The physics is sound. But can it happen on a planetary scale? According to one modeling study, the right carbon-to-oxygen ratio in the protoplanetary disk could lead to such compositions. Yet no direct confirmation exists. We hover in the space between evidence and imagination. Simply put, a diamond planet would not glitter. It would smolder. Its surface might be oceans of magma, black glass crusts cracking and reforming. Its mantle would be less like Earth's silicate rocks and more like compressed carbon, layered into structures we cannot fully simulate. Heat flows, convection, and volcanic cycles would differ completely. Why does this matter? Because it shows us how initial conditions in the nursery of a star system dictate destiny. If Earth had formed with more carbon, its geology, atmosphere, and perhaps even the possibility of life would be rewritten. Think of it like this. Take coal, press it under unimaginable weight, and stretch it across the size of a world. Diamond is not rare when the crucible is a planet. Yet diamond does not mean beauty here. It means density, rigidity, alien tectonics. Human eyes trained to prize sparkle would find nothing to admire. A telescope would see a searing ember, its light modulated as it blazes behind its star. A sensor would read spectral lines that hint at gases torn from rock itself. Observations so far are ambiguous. One research group reported flux variations suggesting an atmosphere of volatile molecules. Another found no such evidence, implying a bare rock glowing in thermal emission. The instruments disagree. Calibration errors, stellar noise, instrumental drift all complicate the picture. Yet even in this uncertainty, the stakes are clear. If 55 Cancri E or others like it hold atmospheres, then rocky worlds under pressure may not be as barren as assumed. If they do not, then the lesson is still vital proximity to a star sets limits we cannot ignore. Our rhetorical questions multiply. How long can a planet cling to its air when tides strip it every orbit? If magma oceans outgas volatiles, do they replenish or vanish into space? If carbon compresses into diamonds, what geology unfolds inside such a globe? Could plate tectonics exist without silicate rock? Or would the crust lock solid? If an atmosphere does survive, what chemistry thrives at such temperatures? Human scale sharpens the contrast. Imagine a world where sunrise never comes, because one face never turns to the star. Stand on the starward hemisphere, and the ground itself glows red, a plain of liquid rock boiling into vapor. Stand on the dark side, and you may find crust cracking under the stress of heat transfer. Simply put, this is not a place for oceans or forests. It is a forge, a crucible, a planet remade into an experiment. One published team noted that infrared phase curves may indicate heat redistribution, suggesting a thick layer of volatile gases. Another cautioned that the signal could come from magma alone. The debate is not settled, but each attempt refines our instruments, improves our models, and prepares us for subtler worlds. What this means is that even a hostile inferno becomes a stepping stone toward understanding habitability. Why does it matter? Because pressure and composition decide a planet's fate. Carbon-rich disks may produce carbon-rich planets. If so, then diversity in exoplanet chemistry is greater than we assumed. If diamonds lurk in mantles, geology across the galaxy is stranger than geology here. It matters because it stretches our expectations, forcing us to test theories of planet formation against a wider sample. It matters because what seems extreme at first may prove common in the census of worlds. At its core, this chapter is about pressure, not just the physical crush of gravity, but the conceptual pressure on our ideas. We assumed rocky planets would echo Earth, with silicate crusts and iron cores. Now we face planets that could be entirely different in composition, yet still stable, still orbiting, still planets by any definition. The contradiction is that they are both familiar and alien. They orbit stars, they follow physics, but they rewrite geology. Usul. We step through the gate of carbon with our questions still open. If pressure can sculpt diamond out of mantle rock, what storms can glass and silicate conjure when hurled across skies of blue fire? The next passage in the City of Impossible Worlds leads us into a storm painted blue. But the color is a deception. At first glance, HD 1189733b appears the shade of oceans, a calm azure globe, drifting in a distant orbit. The human mind is quick to imagine seas, skies, and reflections that echo home, yet the instruments say otherwise. Its blue is not from water. It comes from fine silicate particles suspended in its atmosphere. Glass dust scattering starlight into wavelengths our eyes read as oceanic. What looks like tranquility is in truth turbulence, a planet wrapped in storms that fling shards at supersonic speed. The clue began with light curves. As the planet transits its star, small variations in reflected light reveal albedo, the measure of how much light bounces back. One observing campaign found that less than 30% of starlight returns. The spectrum peaks in blue, suggesting the scatter of microscopic grains. These grains are silicates, the same material that makes up sand and rock on Earth. But here they are not settled. They are lofted high into the atmosphere, forming clouds of glass. According to one widely cited study, the winds on this planet blow at over 7,000 kilometers per hour. At those velocities, the grains cut sideways across the sky, propelled like invisible knives. In plain terms, imagine standing in a storm where every raindrop is a fragment of ground glass and the wind moves faster than sound. To survive such conditions is impossible. To measure them from light years away is astonishing. Our telescopes, orbiting above Earth's atmosphere, catch the tiny changes in brightness as the planet shows first its day side, then its night. From that pattern, we extract not just color but circulation. The bright side is hot, the dark side cooler, but heat flows in massive rivers of air, transporting particles and creating permanent storms. Simply put, the blue world is not calm, it is brutal, where we associate blue with depth and peace. Here it means abrasion and violence. The contradiction lies in perception. The loveliest color hides the most hostile weather. Why does it matter? Because it forces us to confront bias. We cannot assign habitability or comfort by color. Our senses are tuned for Earth. But the universe speaks in a dialect that often reverses meanings. Think of it like this: a stage lit by blue lamps. The performance looks serene, but behind the curtain machines roar, metal flies, and knives fall like rain. HD 1189733b is that stage. The light is theater. The atmosphere is chaos. Our instruments are the audience, parsing the performance second by second. Each photon is an actor, each curve of brightness a line in the script. The observations deepen the contradiction. One group detected methane in the atmosphere, though later data questioned the finding. Another saw signatures of water vapor mixed with silicates. If true, the chemistry is both familiar and alien molecules we know, surviving in conditions they should not. How do they endure at thousands of degrees? Are they replenished from below, or shielded by clouds? The questions remain open, but even disputed detections matter because they sharpen instruments, refine models, and remind us to doubt easy answers. Our rhetorical questions accumulate. What does blue mean if oceans are absent? If methane can exist in storms of glass? How stable is chemistry under extremes and wanes at 7,000 kilometers per hour shape landscapes? Or do they erase landscapes entirely? If clouds are made of rock, what else might masquerade as sky? Does the presence of familiar molecules in hostile places hint at resilience or at coincidence? Human scale helps anchor these extremes. Imagine walking into a gale that tears skin in seconds. Imagine the air filled not with mist, but with shards of silicate that cut like blades. Imagine a day that never ends, because the planet is tidally locked, with one face in constant glare and the other in eternal shadow. Simply put, these images show how alien conditions push the word weather into new territory. One published analysis concluded that the planet's low albedo supports the case for hazy particle-filled clouds. Another emphasized the enormous wind speeds as the likely explanation for the shifted heat signatures. Together, these studies confirm that what we see as color is not a cosmetic feature, but a physical process. The planet's hue is a byproduct of mineral dust, flung skyward and held there by relentless circulation. The blue is evidence, not ornament. Why does this matter? Because color becomes data. Aesthetic impressions are no longer aesthetic alone. They are chemistry written in light. If we misread blue as water, we misread potential habitability. If we learn to decode blue as silicate dust, we gain a tool for interpreting distant worlds. It matters because every misinterpretation corrected sharpens our ability to search for the rare places where liquid water, and perhaps biology, could exist. At its core, this chapter is about perception tested by physics. Our eyes want to see oceans. Our instruments insist on glass. The contradiction forces humility. We cannot trust appearance. We must trust measurement. Yet the beauty remains, now deepened by knowledge. The blue is not less striking because it is violent. It is more striking because it is true. We close this gate with sharpened vision. If color can betray us so thoroughly, then habitability itself may be a mirage. Ahead lies the next threshold, where the very zone we call just right shifts with time and threatens to vanish beneath the glare of a brightening star. The fourth gate opens into a landscape that at first feels reassuring, a planet much like Earth in size, circling a star not too different from our own. Sits in the celebrated region called the habitable zone. This is the ring where temperatures could, in principle, allow liquid water to exist. To many, it looks like home from afar. Its orbit lasts about 385 days, only slightly longer than our own. The temptation is immediate. Could this be a second Earth, a mirror waiting in the dark? Yet the closer we look, the more fragile the picture becomes. The habitable zone is not fixed. It drifts, shifts, and sometimes vanishes. The supposed comfort turns out to be a mirage. The clue is light once again. A faint star dims in precise rhythm, revealing the silhouette of a rocky planet. Calculations show its radius, its distance, and its star's energy output. All appear to fall into the right range. The numbers make us hopeful, but the contradiction surfaces quickly. Stars change with time. Their luminosity grows as they age. A planet comfortably within the habitable zone today may find itself baked tomorrow on cosmic scales. One research group estimated that for certain stars, the safe zone moves outward by millions of kilometers every billion years. A world that once promised oceans may end up cloaked in steam. In plain terms, a habitable zone is not a place. It is a moving ring painted by a star that refuses to stand still. We cannot treat it as a permanent address. To map it is to map something in motion, like drawing boundaries on the surface of a river. Simply put, habitable is a snapshot, not a guarantee. The mirage is powerful, because the word suggests permanence. The truth is that climate depends on both space and time. Think of it like this. A desert traveler sees water shimmering on the horizon, approaches, and finds sand. The habitable zone can be that kind of vision. From a distance, the numbers suggest safety. Up close, heat or cold undercut the promise. The concept remains useful, but we must treat it with caution. Our senses and our models are equally prone to illusions. The debate over Kepler 452b illustrates the problem. Discovered in 2015, this planet was celebrated as Earth's cousin, Earth's twin, Earth 2.0. It circles a sun-like star in the habitable zone, with a year similar to ours. Yet the star is older, perhaps 1.5 billion years beyond the sun. Its increased brightness may already have driven the planet into a runaway greenhouse, like Venus on a slower fuse. According to modeling studies, the planet could once have been temperate but is likely now hostile. The announcement headlines promised another Earth. The details told another story. Our rhetorical questions sharpen. How many of our celebrated Earth twins are actually Venuses in waiting? If time erodes habitability, is life's window narrow or broad? Could civilizations rise and fall in spans too brief to register in stellar terms? Is the very idea of a habitable zone misleading, distracting us from more complex measures? What if biology thrives, not in narrow rings, but in niches we have yet to imagine? Human scale offers perspective. Imagine Earth 1 billion years from now. The sun brightened by 10%, oceans boiling into steam, forests replaced by deserts, seas turned into skies. Life today depends on a delicate balance that will not last forever. Simply put, habitability has an expiration date, even here at home. To project permanence onto distant planets is to forget our own fragility. One published analysis highlighted that the inner edge of the habitable zone is not a sharp boundary, but a gradient. Planets near this edge may undergo runaway greenhouse as small shifts in stellar output push them over the threshold. Another emphasized the role of atmospheric composition. A thick carbon dioxide atmosphere may extend habitability outward, while thin air shortens it. Together, these studies remind us that habitability is complex, conditional, and unstable. The label Earth-like is at best provisional. Why does this matter? Because the search for life depends on more than orbital distance. We must consider stellar age, variability, planetary mass, atmospheric makeup, even geological feedback. The mirage matters because it trains us not to be fooled by simple categories. If we overtrust the habitable zone, we risk misclassifying barren worlds as promising and ignoring outliers where life might truly exist. It matters because it reveals the limits of shorthand, forcing us to deepen our criteria. At its core, this chapter is about humility. We built the idea of the habitable zone as a first tool, a yardstick to guide surveys. It was useful. It still is. But reality stretches beyond. The contradiction is that while we celebrate each new Earth candidate, we also learn that many are mirages, promising more than they can deliver. Our instruments map them, our models revise them, and our expectations bend under pressure. The mirage has one more lesson. Even if a planet falls out of the habitable zone, it might still harbor life if internal heat, tidal stress, or chemistry sustain it. Europa, Enceladus, and other moons in our own system remind us that liquid water can persist beneath ice, far from the sun's warm band. To put it another way, life may not care about our neat rings. It may flourish in places our categories overlook. The gate of habitability is not a doorway to paradise, but a mirror reflecting our hopes and our errors. We step through it with greater caution, ready to redefine the very metrics we use to search. The bridge leads onward. If time can turn paradise into steam, what do we find at the edges of theory, where giants exist that should never have formed? The gate opens to a realm where the outlines of our formation models begin to fray. Here, planets swell into giants so large and so remote from their stars that the blueprints of planetary birth no longer fit. We thought we knew the process. Dust grains gather into pebbles, pebbles into rocks, rocks into planetesimals. Cores grow heavy, and only then do they pull gas around themselves. But what happens when a world 3 times the size of Jupiter hangs at a distance where raw material should have been too sparse to build it? The contradiction is sharp, and it calls into question the boundaries we have set between planet and star. Direct imaging provides the first clues. Unlike most exoplanets found by the transit or radial velocity methods, these giants appear in photographs, faint dots glowing in the infrared beside their stars. One young object, catalogued around a star just a fraction the sun's mass, shows a bulk that rivals or exceeds Jupiter, yet it sits tens or even hundreds of astronomical units away. According to several observing teams, These companions are far too massive and too distant for the slow core accretion process to explain. Something else must have happened. In plain terms, these giants are shipwrecks on the map of theory. The shipwright's plans do not show them. The lumber is missing. The nails are absent. Yet somehow the hull floats. Simply put, they force us to expand our imagination. If they did not build slowly, perhaps they collapsed quickly. Clouds of gas fragmenting under their own gravity before a core ever formed. That mechanism, known as disk instability, blurs the line between planet and brown dwarf. Are we looking at failed stars or overgrown planets? The categories start to dissolve. Think of it like this: an unfinished shipyard at the edge of a bay, spars scattered, tools abandoned. Yet there in the water lies a massive vessel, complete enough to sail. No plan explains its presence. These giants are that vessel. They loom where our theories left nothing, and their very existence asks how incomplete our construction diagrams really are. One research group notes that the cooling rates of such objects suggest youth, glowing heat left over from formation. Another argues that their colors imply heavy element enrichment, hinting that cores did exist at some point. The debate persists, fueled by new data. None of the explanations is fully comfortable. If disk instability dominates, why are such giants not more common? If core accretion can still apply, what hidden process allows cores to form so far from the furnace of the star? Our rhetorical questions sharpen. What defines a planet if its birth echoes that of a star? If mass alone blurs categories, do we need new labels? How do orbits tens of times wider than Neptune's persist without being stripped away by stellar neighbors? Could these giants harbor moons? And if so, what climates would orbit such improbable parents when theory cracks? Do we patch it, or do we redraw it from scratch? Human scale brings perspective. Imagine a world so far from its star that the warmth of sunlight is weaker than twilight on Earth. Yet the planet glows faintly of its own accord, heat left over from birth. Picture standing on a moon circling such a giant. The star a distant ember, the horizon dominated by the globe of the planet itself, a looming sky larger than anything we know. Simply put, these images remind us that the galaxy does not honor our categories. It builds as it pleases. One published analysis compared the spectra of these giants to brown dwarfs, noting striking similarities. Another emphasized differences, particularly the apparent enrichment of heavy elements that might anchor them more firmly in the planetary family. Together, these studies illustrate the tension evidence points in both directions. The giants at the edge of theory are hybrids, resisting simple classification. Why does this matter? Because categories shape our search. If we cannot define planet and star clearly, our statistics on formation, frequency, and survival blur. Understanding how giants form far from their stars helps refine our models of how smaller, more common planets form closer in. The extremes test the rules. Without them, we risk mistaking local exceptions for universal truths. At its core, this chapter is about limits. We built theories that worked for the solar system. They work for many other systems too, but the exceptions multiply. Each giant at the edge of theory reminds us that our knowledge is provisional, a scaffold built to be expanded, sometimes torn down. The contradiction is that these remote giants are rare, but even one demands revision. The universe does not need to provide many counterexamples to shatter certainty. The shipyard is not empty after all. It hides constructions we did not anticipate, and they sail whether or not our diagrams account for them. Ahead lies another gate, one where the very star itself reshapes climate, painting multiple summers and winters onto a planet's short and relentless orbit. The next gate opens not onto a planet itself, but onto its star. Most of us think of seasons as planetary affairs, driven by the tilt of an axis. On Earth, the lean of 23.5 degrees turns solstices into cycles of warmth and cold. But here, seasons are painted not by tilt, but by the star's shape. The host is a blue star spinning so fast that it bulges at the equator, flattening its poles into hotter, brighter caps. The planet circles in an orbit of just a day and a half. Instead of a steady flood of light, it receives changing streams depending on which stellar latitude faces it. The result is 4 seasons per orbit, 2 summers and 2 winters in less than 2 Earth days. The clue is light once again. Observations of brightness across wavelengths reveal that the star is hotter at the poles than at the waist, a phenomenon known as gravity darkening. One survey showed that stars rotating rapidly enough can differ by thousands of degrees between equator and pole. A planet orbiting such a star does not bathe in uniform radiation. Instead, it sails across stripes of temperature, alternately scorched and dimmed. For the orbiting world, climate is not written by planetary geometry, but by stellar spin. In plain terms, imagine circling a lantern whose sides glow unevenly, hot at the top, cooler in the middle. As you move around it, the light on your skin changes without your own posture shifting. That is what happens to this planet. Simply put, seasons come not from tilt or distance, but from the star's uneven glow. The effect is disorienting, but the measurements are consistent. Spectroscopy confirms the temperature gradients. Models show that radiation levels on the planet fluctuate wildly with each pass. Think of it like this: a clock that runs 4 times as fast as you expect, ringing out summers and winters every few hours. Life here would endure constant transitions, never settling, never stable. The metaphor holds the star is the clockmaker, not the planet. The contradiction deepens when we consider atmosphere. Can a world orbiting this close retain gases at such short periods? Tidal forces strip atmospheres and heat bakes them away. Yet some studies suggest thick atmospheres might survive for a time, replenished by volcanic outgassing or by sheer gravity. If so, the climate would be a chaos of expanding and collapsing envelopes of air, boiling on one side, condensing on the other, repeating every orbit. According to one research group, the mass loss rates of such planets may be high enough to sculpt tails of gas, like comets bound by gravity. Our rhetorical questions sharpen. How long can a planet endure 4 seasons in 40 hours? What does stability mean when cycles move faster than biology could possibly adapt? If the star writes the seasons, does the planet lose its agency? Could life, in any form, find a foothold under such rapid change? Or are these worlds sterile laboratories, meant only to test our physics? Human scale illustrates the strangeness. Imagine a single work shift that includes summer heat, winter chill, then summer again before you go home. Imagine weather forecasts measured in hours, not months. Imagine the ground beneath you heating and cooling in relentless pulses, metals expanding and contracting with every cycle. Simply put, the rhythm would break every habit of biology we know. One published analysis of Kelt 9b, a giant orbiting a hot star, showed evidence that its atmosphere is being stripped under extreme ultraviolet radiation. Another reported that its orbiting conditions subject it to more than 10,000 times Earth's radiation. Together, these results emphasize that close orbits around hot stars are places of violence, yet they are measurable. Instruments capture spectral lines of hydrogen escaping, confirming the presence of comet-like tails. These data transform speculation into evidence. Why does this matter? Because it proves that stars can dominate climate in ways we did not predict. Seasons are not always planetary. Habitability depends on stellar physics as much as planetary parameters. This matters because it expands our search for life, forcing us to consider star-planet systems as wholes, not separable parts. It matters because it reminds us that stability is fragile, and that even small shifts in stellar behavior can rewrite planetary climates entirely. At its core, this chapter is about the shifting of agency. On Earth, the tilt of our axis defines our seasons. Here, the star dictates every rhythm. The contradiction is that a planet may exist, orbit, and persist, yet never experience a stable climate. The star's spin overrules planetary identity. The Gate of Seasons teaches humility. We cannot assume cycles of growth and rest are universal. We cannot assume that comfort zones translate across systems. We step forward with this caution in mind. If stars can paint climates with their rotation, then what of planets whose very light curves tell us they are darker than soot, pinker than any sky, or whipped into eccentric orbits that defy stability? The next gate swings wide into a theater of extremes. Here the sky does not shine. Here planets perform feats that make even seasoned theories falter. We find a world darker than coal, another that glows in magenta, and one whose orbit whips like a slingshot. These three cases, tied only by their defiance of normalcy, remind us that nature writes its own catalog. The first clue comes from TRES 2b, a hot Jupiter whose albedo is less than 1%. In measurements of secondary eclipses, when the planet slips behind its star, astronomers find almost no reflected light. The world swallows photons with ruthless efficiency. According to one published survey, it is the darkest exoplanet yet detected. Its appearance is not midnight blue or stormy gray. It is absence, nearly pure. The contradiction is immediate. Giant planets in our solar system reflect. Jupiter shines with bands and storms. Even Neptune gleams. But this one drinks light until almost nothing returns. In plain terms, this planet is darker than the blackest paint we can manufacture. Simply put, its atmosphere absorbs nearly everything, reflecting no sign of the star it orbits. The likely culprits are alkali metals and possibly exotic chemicals that thrive in high heat, capturing visible light and bleeding it out as heat. What does color mean for such a world? If darkness can be measured, then it is not poetic but physical. Human scale can feel this alien darkness. Imagine holding a lump of charcoal under bright light, then imagine something darker still. So dark you feel your eyes tricked. Now multiply that sensation across a globe larger than Jupiter. The mind resists, but the data do not. Next, the stage shifts to GJ 504b, a planet glowing faintly in magenta. Direct imaging revealed its hue. Unlike any planet nearby, it orbits far from its star, yet retains warmth left from formation, radiating infrared as a pinkish glow. Some studies suggest methane absorption helps sculpt the spectrum, enhancing the unusual tint. Again, the contradiction is sharp. Pink skies and magenta worlds were left to artists, not instruments. Yet here they are, written in photons. Think of it like this: a painter's brush dipped in colors never meant for planets. Earth gave us blue seas and green forests, Mars its rust, Neptune its azure. But here, pink dominates, the palette widens. The universe insists we abandon our bias that only familiar hues belong to nature. Then comes the whiplash. HR 5183. B follows an orbit so eccentric that it spends most of its time far from the star, only to dive inward on a trajectory like a comet. Observations from radial velocity methods, gathered over decades, show the star's tug shifting as the planet yanks it in sudden accelerations. The orbit stretches into centuries, yet when it swings close, it drags velocity like a tether pulled taut. According to one team, gravitational scattering with other planets may have ejected neighbors, leaving the survivor with its wild oval path. Our rhetorical questions accumulate. What defines darkness when a planet erases nearly all reflection? How do we talk about color when a gas giant wears pink like a flag? Can stability endure when orbits fling giants inward and outward like stones from a sling? How many of our models collapse if even one such system exists? And how do moons fare if tied to these giants? Living under skies that shift from star bright to star dim in a single season of centuries. Simply put, these cases stretch our sense of order. JWST 2b matters because it proves that darkness is measurable, quantifiable, physical. GJ 504b matters because it rewrites the spectrum of possible worlds, reminding us that beauty is not bound to Earth. HR 5183b matters because it shows violence carved into orbits, evidence of cosmic brawls that last for billions of years. One published analysis emphasized that JWST2b's albedo is lower than vantablack, a material engineered to absorb light. Another compared GJ504b's spectrum to models of methane-rich atmospheres, confirming the plausibility of its magenta glow. A third tracked HR5183b's radial velocity shifts, consistent with a long, eccentric orbit born of scattering. Together, these lines of evidence sharpen our picture. The contradictions remain, but they are not illusions. At its core, this chapter is about extremes of visibility. One planet cannot be seen because it is too dark. Another is seen because it glows in colors we never expected. A third moves so violently that its path becomes a lesson in chaos. Each case undermines categories we took for granted. Each forces us to broaden the language of planets. Why does this matter? Because it breaks our dependence on Earth as a template. Darkness, color, orbit. These are not accidents. They are properties with causes, measurable and repeatable. By studying them, we sharpen the tools that will one day interpret the faint signals of smaller, more fragile worlds. We learn not to be fooled by beauty, not to dismiss strangeness, not to fear the violence of orbital scars. The theater of extremes closes with a challenge. If darkness, magenta, and whiplash can coexist in the same sky of discoveries, then what ancient survivors wait beyond, older than most of the stars themselves? The last gate in this act opens onto a relic, a world so old that its age presses against the very beginning of time as we know it, in a crowded globular cluster, deep in the constellation of Scorpius. Astronomers have found a planet circling not one but two stellar remnants, a pulsar, collapsed to the density of atomic nuclei, and a cooling white dwarf. This world, often called Methuselah's planet, carries an estimated age of 12.7 billion years. That number is staggering. It means the planet formed just a billion years after the Big Bang, when galaxies were still coalescing, when heavy elements were scarce, and when life as we know it was not yet imaginable. The clue is subtle. Pulsars flash with clockwork precision, their beams sweeping past Earth like cosmic lighthouses. Any planet orbiting them tugs on the timing, causing shifts in the rhythm. One group of astronomers measured those deviations and deduced the presence of a companion planet. The mass and distance fell into a range that confirmed it was not a star, but a planet-sized body. The evidence was strengthened by models of the white dwarf cooling age, which matched the ancient timescale. Together, these lines of reasoning pointed toward a survivor unlike any we had ever encountered. In plain terms, the world is older than our solar system by more than twice its age. Simply put, this planet has existed through most of cosmic history, orbiting long after its parent stars exhausted themselves. While Earth's continents have shifted, oceans risen and fallen, and species appeared and vanished, this distant planet has continued its orbit around the corpses of suns. Its very survival is a paradox. How could a planet endure through the violent death throes of its stars? Why was it not consumed, shattered, or flung away into interstellar darkness? Think of it like this: a library fire rages through the shelves, consuming nearly everything. Yet on one table sits a single book, charred but intact, still legible. The oldest survivor is that book. Its pages are worn, its cover scorched, but its story persists. We cannot yet read its text in full, but we know its age by the fading of the ink. The contradiction is profound. Planet formation requires heavy elements: carbon, oxygen, silicon, iron. Yet at such an early epoch, those elements were scarce. Stars had only begun forging them. For this planet to exist, it must have formed from the earliest seeds of enrichment, when the universe was still poor in metals. One published analysis argued that globular clusters, despite their ancient age, may still provide pockets dense enough for planets to condense. Another countered that the planet might have formed later, captured into orbit after the pulsar and white dwarf came to be. The debate remains unresolved. Our rhetorical questions multiply. How many other ancient planets lurk in globular clusters, waiting for us to notice their subtle signatures? If planets could form so early, does this extend the possible timescale for life far deeper into the past? Could any form of chemistry have thrived on such worlds before our sun was even born? And what does it mean for us? As latecomers in the cosmic calendar, if habitable conditions existed long before our planet emerged, human scale sharpens the awe. Imagine Earth erased, our solar system gone, yet a planet continuing to circle its dead suns for billions of years beyond. Imagine a civilization, had it existed there, watching entire generations of galaxies collide while their own world kept orbit. Simply put, survival here is not luck. It is testimony to stability we had not thought possible. One team analyzing pulsar timing suggested the planet's orbit is stable enough to have survived 2 stellar deaths. Another calculated that its mass and distance keep it bound despite the explosions. Together, these studies confirm that resilience is written not just in stars but in their companions. The evidence is strong, but the mystery remains. Was the planet truly born with its stars, or was it captured later, drawn into the dance by gravity? Either way, it is old beyond measure. Why does this matter? Because it redefines the timeline of planetary formation. If planets can form, or persist, this early, then the universe may have been building potential homes for life, far sooner than we expected. It matters because it stretches the window of possibility, suggesting that life's opportunities may not be confined to a narrow slice of cosmic time. And it matters because survival itself becomes data. The oldest survivor tells us that orbits can endure catastrophes, that worlds can outlast suns, that stability is broader than we thought. At its core, this chapter is about endurance. Our theories assumed planets belong to stars in their prime. Here we find a world loyal even to stars that have died. The contradiction is that planets, fragile as they seem, may outlive their creators. They become fossils, archives, silent witnesses to the universe's earliest chapters. This is the biggest reveal of all. The existence of such an ancient planet tells us that worlds are not recent ornaments, but fundamental components of cosmic history. From the first billion years onward, the universe has hosted planets. The baseline is not rarity, but abundance. The cosmos is not waiting to make worlds. It has always made them. For more insights like these, remember to like and subscribe to the Quiet Universe channel. The bridge ahead carries us out of the city of strange planets and into a final chamber where philosophy takes over, where we ask not only how planets form and survive, but what it means for us to be thinking beings in a universe that prizes strangeness as its norm. The city of impossible worlds is now behind us, but its echoes follow. We walked through gates of light, of heat, of time, of color. We saw iron rain where weather becomes metal, diamonds where geology becomes lattice, blue storms where glass falls like knives, mirages of habitability where time erodes hope, giants born at the margins of theory, climates painted by stars, extremes of darkness and magenta, and a survivor older than most galaxies. Each step showed us that normal is not the baseline. Strange is, we return now, not to recount, but to listen to the deeper undertones. Every discovery carried more than data. Each bore a message. Our categories are too narrow, our definitions provisional, our vision incomplete. The paradox is that the more we measure, the less room Earth has to remain typical. If we had clung to a belief in planetary uniformity, the universe has corrected us. It insists that diversity is its law. One research group phrased it cautiously: exoplanet science is less a catalog of exceptions and more a ledger of possibilities. Another reminded us that the sample size continues to grow. Thousands of worlds now confirmed, and each adds weight to the conclusion that the ordinary is an illusion. These voices echo not just as statistics, but as philosophy. When exceptions outnumber the expected, what is the true definition of normal? In plain terms, we are latecomers discovering that the universe has been building planets from its earliest days. We assumed the conditions for Earth were rare. Simply put, they may be common in outline, rare only in detail. Think of it like this: a library where every book is bound in different material, written in different scripts, yet all belong to the same collection. Earth is one volume, not the template for the rest. The oldest survivor makes the echo sharp, a world orbiting a pulsar and a white dwarf, nearly as old as time itself, whispers that planets are not ornaments but foundations. If planets can arise when heavy elements are scarce, then the timeline for habitability is longer than our own story. Why should we assume that intelligence is confined to late epochs? Could consciousness have sparked long before us, leaving traces we do not yet recognize? These are questions with no present answers, but their weight shifts our posture. We are not pioneers at the dawn. We are children arriving late to a gathering already in progress. Human scale grounds the immensity. Imagine holding a pebble from your childhood pocket and realizing it is older than continents. Imagine standing under a sky that has looked the same for billions of years, while entire civilizations, had they existed, might have risen and fallen unseen. Simply put, time dwarfs us, but it also invites us. If worlds endure longer than stars, then meaning must be found not only in beginnings, but in persistence. One recent analysis of globular clusters suggested that stable orbits may exist even in such dense star fields. Another found that even ancient metal-poor stars can host giant planets. These results expand possibility. They tell us that planetary systems have been part of the universe's architecture from near the start. Our place is not unique. It is one entry in a cosmic ledger too vast to read in full. Why does this matter? Because the search for life is not just science. It is reflection on meaning. If the universe is filled with planets, then silence becomes more curious, not less. Are we listening incorrectly? Or is intelligence rarer than the stage on which it might arise? Why does it matter that iron rains on some worlds? Because it shows physics is consistent. Why does it matter that planets survive their stars? Because it shows endurance can be greater than brilliance. Why does it matter that so many defy our categories? Because it shows humility is the first step to knowledge. At its core, the echo is not about planets alone. It is about us. We built a map of reality shaped by Earth. The universe tore that map and handed us fragments larger than the original. The contradiction is painful, but liberating. When definitions break, imagination grows. When norms collapse, new frameworks rise. If planets can be darker than black, pinker than any palette, older than suns, then our own existence is neither central nor final. The echo grows quiet, leaving one strong line to carry. We revise our laws, not because the universe changed, but because we finally looked. That is the lesson every exoplanet whispers. Observation is humility made visible. Knowledge is not discovery of new laws, but correction of our illusions. We close with an image. The camera drifts from the crowded heart of a globular cluster outward. Dead stars pulse like clocks. A lone planet circles, its orbit steady across billions of years. Beyond, blue giants paint their seasons on fleeting worlds. Further still, a magenta ember fades in a long arc. Darkness swallows light, yet the story endures. And so the final question lingers: if strangeness is the baseline, what kind of minds must we become to call such a universe our home?